Okay, so this talk will serve a dual purpose of introducing the Minnesota Space Grant, and also just sort of in general and logistical terms. It turns out that the Minnesota Space Grant includes about a dozen or so schools in Minnesota formally, and Winona State University is not on that list. On the other hand, we're very interested in talking to you and learning about what you do and having you learn about what we do to see if it makes sense for us to work together on projects either informally or possibly formally at some point. So besides sort of a logistical introduction, I'd also like to show you some of the things that we do here at the University of Minnesota Twin Cities campus. We are the lead institution in this consortium, and one thing I like to try and do at least is take a crack at various topics and then see if I can talk other people around the state into following suit. I don't necessarily propose things that I haven't tried myself. So this particular rather busy screen just shows pictures. Let's see, can you see my cursor? Yes, you can. So basically here, for instance, are weather balloons, which allow us to take things up into the stratosphere and get into this kind of an environment, which is sort of a space-like environment. Here's a picture of some students who are, I lost my cursor, sorry. Above that is a picture of students working on a quadcopter project, and it turns out that Winona State is in fact currently involved in a quadcopter project that we are sponsoring. And then on the left-hand side of the screen are some students who have built a specific kind of rocket. This is called a high-power rocket, sort of a step up from model rocketry. And these rockets can not only carry sensors and whatever, but they can also carry cameras. So that one picture there shows such a rocket, not the one in the lower picture, but such a rocket as it starts to come apart in flight so as to deploy parachutes. And the students in that picture are actually from a freshman class. This was a freshman seminar that I taught here. So I actually want to start with a video before I dive into my main slides. So let me step away from this for a second and click over to this 3D video. So here, this video actually shows the launch of a weather balloon, and this is 3D, so I can actually poke around after the fact and see the fact that this camera is mounted on a payload that's about to be flown by a balloon. Notice this balloon, at least from this perspective, doesn't look too much bigger than the payload above it, and that's going to get a lot bigger during the flight. Here are a couple other balloons ready to be launched. If I click play here.
5, 4, 3, 2, 1. See ya.
So basically, this is just the launch of a pair of weather balloons. This was actually done in the summer of 2017 during a total solar eclipse. It's not totality yet. In fact, you can't tell yet that there's an eclipse coming. But if I forward partway into this video, and now we're above the cloud decks and getting into the stratosphere, and there we see on the horizon the shadow of totality approaching us. And if I go a little bit farther along, now we are actually in the shadow of totality. And so no matter where I look underneath me, I see darkness. And then of course I see darkness above me because we're getting above the glow of the sky. And then notice that that balloon is now significantly larger. Now, it turns out you can't do this every day. In fact, and there's the sun. The sun has not disappeared altogether. The sun is just very, very muted because you're seeing the corona of the sun. This particular camera is not zoomed in so as to be able to focus on the sun and see the details. But even when the sun is a tiny, tiny, tiny bit exposed, like here, this is 99.99% covered, and yet it's already too bright for the camera to deal with. But one thing I like to point out about this particular footage, besides the fact that it's very cool to see that shadow go by at more than 1,000 miles an hour, is that this is the environment. This is later in the flight. The shadow is gone. And frankly, this is where we can go with this kind of a platform any day of the year. In fact, I did my most recent flight last weekend, as in a week ago, 8 days ago. And so if there is interest on your end of flying things in this environment, whether it's for remote sensing of the Earth or just for fun, shall we say, or putting on sensors of various sorts to study the atmosphere, or from this perspective, you can't really do photography because the platforms, astrophotography, because the platforms aren't stable enough for that. But anyway, so this is an example, and there's the balloon. It's gotten a whole lot bigger and it's about to pop, but I think I won't. I think I'll stop the video now and go back to my slides. I consider that sort of a classic a classic space grant project in the sense that it was interesting, it was motivational, it got people interested in, hopefully interested in space or NASA sort of activities, but it didn't necessarily do something that was research grade. It could have, perhaps, but that was not the point of that particular activity. So let me hide this panel again and go through a few slides of notes. Okay, so just some historical notes about Space Grant in general. If I can get this to forward, come on. Here we go. Okay, so Space Grant, which is technically called the National Space Grant College and Fellowship Program, was established in the late 1980s. And the intention was for NASA, which had higher education funding, to spend it not just in Texas and California and Florida, which are the places that they have their biggest launch facilities. So it makes sense for them to spend it in those states. But this was an attempt to get them to spend it farther around the country. So now there is a space grant in every state, including as well as DC, as well as Puerto Rico. So there are actually 52 of them. Here are some sort of general statements about space grants. One is that they are led by some institution, typically a large university. They have affiliates. And so the affiliates come in sort of two flavors. There are the academic, the college university affiliates, and this is a college program. And then there are the non-academic affiliates. So typically those would be things like science museums or state government or whatever. And all space grants will also actively try to work with other non-affiliated colleges and universities and schools and industry and general public. And so the Minnesota Space Grant in particular was established in 1989, 1 year after the original program, which only included half the states. And right now it has 12 academic affiliates and 1 governmental affiliate, which is MnDOT Office of Aeronautics. And here's our website, and I would encourage you to spend time looking around there to see who's involved and what they do. So my next slide will show where the affiliates, the current affiliates, are located. They're around the state. Here are the 12 academic affiliates. About half of them are in the Twin Cities metro, and we are the lead institution. And about half of them are spread around the state. We cannot possibly touch the entire state, but we have reasonably good coverage. And it turns out that we do activities in addition to the affiliates with the following institutions. So Century College, Normandale, St. John's, University of Minnesota Morris, University of Minnesota Crookston, Moorhead, Minnesota State Moorhead, and Winona State, as well as some physics teachers are actively engaged in some of our programming at the present time. So this is basically who we are, where we are. And now let's talk a little bit about the kind of money we have. So the funding we get from NASA is spread into the following categories. It's about $700,000 to $800,000 a year. So depending on whether you think that's huge or not, about 1/3 of it is set aside for this category, the category of internships and fellowships and scholarships. We call that the NIF category. And so NIF money tends to go to NASA centers, as in Minnesota students going to NASA centers in other states. And that's open to all students, including students from your institution, as well as fellowships, scholarships, internships for students who are attending our schools. And so that would not be actually open to students at your institution, since you're not currently an affiliate. This is our most important area, higher education. So we are a higher education. So this is curriculum development, NASA-themed activities, classes, extracurricular activities for college students and college faculty. In this case, I'm using college to mean college and university. We also do some research, but our research proposals have to be closely tied with what's going on or of interest to people at NASA centers. And the current rule is that research proposals must come from faculty within our schools, although they could potentially involve faculty and students elsewhere through collaborations. We do some pre-college, and so to us pre-college doesn't mean so much pre-college students, but rather pre-college teachers. So teacher workshops, professional development, and then everything else, informal education. So NASA-themed school visits, exhibits, we go to the state fair, except when it gets canceled, things like that. Those are our funding areas. And one of the important rules to make the money go farther is that all money that comes to the state, except for the NIF money, needs to be matched by the recipients. In other words, you've got to put in your own money, or at least your own in-kind effort, to make the money go basically twice as far. And there are some restrictions on how space grant money can be used. Some of them are fairly obvious. This is a US government program, and so we're not allowed to pay non-US citizens. We're not allowed to pay for international travel, and we're not allowed to buy buildings and capital equipment. And coincidentally, we're not allowed to buy computers either. So there are not many restrictions, but there are some modestly important restrictions for us to watch for on the funding side. Here I've just grayed out the two things that are not very available to people who are not within the consortium. But frankly, that was only two out of a rather long list. And so we're anxious for people to give us ideas and to work with us and to help us do this kind of work, especially the higher education part of it. So here's a few other notes. I already mentioned this, but higher education is sort of central. We are called a higher education program, not a research program. This is the hardest thing for faculty, frankly, to understand. We're not supposed to support research. At least that's not the main thing. We're supposed to support curriculum development, and we're supposed to support out of extracurricular rocketry activities and things like that. That's really what we're supposed to do. We do some research, but higher education is more important to us. Engagement of women and underrepresented minorities is very central to what we do and pushed upon us by NASA all the time, and we have to report on how well we do on that. And that's well, we're pleased to do that, and frankly, that's not always so easy. We offer training workshops to teachers and also to college students and faculty to get them started on some of these projects, for instance. We are open to collaboration, especially in our research areas, so people who get Minnesota Space Grant money to do projects are encouraged to pay attention to other people that they can learn from, even if those people aren't necessarily at schools that are within the consortium. And then we, as in Demos and I, the administrators of the program, are interested, frankly, in talking to anybody who has ideas for us about how we can further our goals. And so we are most interested, not unexpectedly, in things that complement as opposed to duplicate the stuff that we're already doing. But we're pleased to talk to people. So what I want to do right now quickly is I want to just show you a bunch of mostly higher education projects. In fact, mostly things that I have personally done. I am the sole employee of the Minnesota Space Grant. And so Demos is a standard faculty member, and he oversees the program and he serves as director. And I am the one person who's actually hired to do this as my actual job. So in higher education, this is just a repeat from the earlier slides. We do curriculum development. We try to support and maybe invent NASA-themed classes. And we also support extracurricular activities, not all of which, but some of which are competitive, like intercollegiate competitions. Here, for instance, are some pictures of high power rocketry. So I mentioned high power rocketry already. Basically, this is a step above model rocketry. And in fact, you need to be certified before you're allowed to purchase the motors. So if you've ever built a model rocket, you might remember that the motors are about as big as your finger. And sometimes they're only half full, and sometimes they're full of fuel. And so they might be called an A motor or a B motor or a C motor. And every time you change a letter, you double essentially the amount of energy in the motor. And so most model rockets fly on A or B or C motors. But by the time you get up to F and G motors and H motors, H is where high power starts. In some sense, it's weapons grade by the time you get that high. And frankly, the government starts to worry about people having that much energy inside a small package. So you need to be certified to purchase H motors for high power rocketry. And so here are some pictures. These are from freshman seminars. We also run a high power rocketry competition. I'll tell you a little bit more about that in a minute. And you know, I didn't try this before coming online, but let me just see if I can get this to play. Click. One moment. One moment. Don't want that, sorry. Wow, I don't know what happened there, sorry. Here's what I want to do, just give me a moment. My apologies that I'm struggling here a little bit because I'm on a different computer than I usually use. My normal laptop died, and that was inopportune. So here's a 49-second video, if I can get it to play. This shows a set of students. These happen to be freshmen. They built approximately a 7-foot tall rocket. That guy in the back there is about 6'3". Here's what it looks like.
5, 4, 3, 2, 1.
Experience. The pad camera. And then here's an onboard camera. So you can hear the computers operating. And again, the rocket starts to come apart and deploy its parachutes. So we do high power rocketry, both in class for freshman seminars upon occasion. I haven't taught one of those, that particular topic, for a couple of years now. But we also have an extracurricular rocket team who's quite active, and the rocket team in particular often will enter, for instance, competitions. We run a competition here and bring in people from around the nation to do our competition, but our teams often travel far away, sometimes to the desert Southwest, to enter competitions and build even bigger rockets than these ones. These are sort of H motor or I motor rockets, and our students sometimes get up to M and N motor rockets. I already mentioned the fact that we do stratospheric ballooning, sometimes in classes. Sometimes I also have an extracurricular stratospheric ballooning team. And you can take this in a variety of directions. It's very interesting, I think, to build these things, to think carefully about how to make sure they operate properly in this difficult environment, which is very much like outer space, and to collect data. Even if you are not planning to do anything sort of research purposed with this data. On the other hand, you definitely could. You're interested in geology, you can do a lot of remote sensing from these platforms. There are just going to be limitations on how heavy the things can possibly be. And then you want to make sure that you fly them in a manner that you can get them back, assuming that you don't have data telemetry, although that's also a possibility, radio telemetry, but rather just onboard logging and then recovery of the packages after they come back down. We regularly fly in southern Minnesota. I think if I was located at your campus, I probably wouldn't launch from there because things would tend to drift into Wisconsin that's heavily wooded, but rather I would drive significantly to the west and let things drift back to the east, closer to landing, closer to where you're located. But one way or another, you're going to have to do some driving if you want to get involved in stratospheric ballooning. Another build topic is radio-controlled airplanes. I'm not actually involved in this one myself, but I sort of got someone else to start one of these classes and teach it to freshmen pretty regularly. This is done by our UAV lab, Uninhabited Aerial Vehicles lab, and they do a variety of things with both fixed-wing aircraft and drones. And so they regularly teach a class every year to freshman students on radio-controlled aircraft. I, on the other hand, since I had familiarity with balloons, decided to teach a class on radio-controlled balloons. So lighter than air radio-controlled vehicles. Here are some pictures of some of the vehicles that we built and flew within our building a year and a half ago, approximately. And so this is a very interesting topic. In fact, I kind of didn't know enough about the history of this until I started teaching it. But man alive, back in the 20s and 30s, I mean, people talk about Lindbergh and how Lindbergh crossed the ocean. You may not realize that there was regular passenger traffic, air passenger traffic across the Atlantic before Lindbergh, okay? But what he did was he flew in a fixed-wing aircraft by himself, and that's what made him famous. But basically the Zeppelins and blimps from the early 1900s were astonishing vehicles, I think, and underappreciated these days. We also built cubesats. So cubesats essentially are spacecraft, and cubesats are 10 centimeters by 10 centimeters by 10 or 20 or 30 centimeters, so they're very tiny. And I tend to have students build cubesats that are functional but not made of space-rated materials and fly them on balloons, just to see how they do. Demos, on the other hand, is involved in actually building cubesats that go into outer space. And so we launched, well, we didn't launch, we sent out to launch our first CubeSat, Socrates. It was on the International Space Station as of 1 year ago and thrown overboard last February, if I remember correctly. And if you want to know more about that CubeSat and other CubeSat projects for outer space, you can ask Demos about those. But anyway, so that's kind of high end, and frankly, that's definitely verging on, and in fact, definitely encroaching on research, as in trying to put things in outer space to actually do genuine research topics. In the case of Socrates, this CubeSat, one of the things it was to do was to try to replace GPS satellite GPS messaging, so that if you are far away from the Earth and you don't have access to GPS, you can still figure out where you are based on listening to astronomical sources like gamma ray bursts and stuff like that. Let me tell you a little tiny bit more about eclipse ballooning. So basically, the eclipse of 2017, I already showed you a little footage of this. There was a nationwide project to put up balloons along this entire track. This was actually the first coast-to-coast eclipse since World War I. So frankly, these are not very common. And the next couple are coming up in a few years. I'll tell you about them in a moment. But we put together a nationwide project that involved many space grants and more than 50 teams. And so I was one of the sub-leaders. I was not the leader. The leaders came from the Montana Space Grant, but myself and several other states were kind of right below them in organization. And so what we did in this particular project is we set up payloads that would fly and then would send down video telemetry, video that they were taking by telemetry, so we could see these things and post them and have people see this view in real time. The footage I showed you earlier actually was not from one of the telemetry cameras. It was from a better camera than that, but we did get some of our imagery to the ground in real time. But unfortunately, there were internet outages along this entire line because so many people were trying to do video streaming, and so we weren't able to actually post it in real time. But here's some information about the telemetry system we put together. And so we had ground stations, we had flight units, we had anti-rotation devices to try and keep our videos from spinning so much. And here's a picture showing the 5 balloons that we launched on that day. And I just showed you images of number 2 and number 3. I'll take it back. Number 3 and number 4 being launched. Number 1 and 2 had already gone, and number 5 was launched later. And so here is a picture, literally, of one of the images that we were able to get down from this in real time during this event, and we could see this on the ground. It turns out we're already starting to plan for the next pair of eclipses. There's an eclipse in 2023. It's an annular eclipse. It goes down from Oregon down to Texas. And then there is a total eclipse in April of 2024, which goes also through Texas, but up through Maine. And so neither of these go through here, but it turns out students who are freshmen now will still be around as seniors. And so now is not too early to be thinking about this particular project, and whether it's ballooning or other sorts of eclipse studies, this is definitely something the Minnesota Space Grant will be involved in. A little bit more about our Midwest high power rocketry competition. Like many competitions that were going on during the 2019-2020 year, and we're supposed to culminate in the spring, we had to cancel that one mid-flight, not mid-flight, mid-program. So here are some pictures from our previous competition, the 2018-2019 competition. And so what we do is we challenge students, and people may join from any college around the country, and we do get people. We've had people from Alaska and Utah and Virginia shows up almost every year. As well as schools from around here. And they do whatever we challenge them to do. And so, for instance, one of our recent competitions, and some of these rockets are for that competition, I think there might be 2 different years illustrated in this set of photographs, is we challenge people to build a supersonic high power rocket, which is actually not that hard. You just put a huge motor in and off you go. But then we said we'll give most points to the person who, or the team that has the smallest or the lightest or the least expensive supersonic rocket. So it had to be the efficient supersonic challenge. And that really gave people fits. And that's good. We're interested in giving people something to think about, something to do. On the other hand, a previous competition where we asked people completely different rules to fly on 2 different motors that are as different from each other as possible and yet reach the same altitude. And it turns out that one of the teams actually figured out theoretically that if they had one of the flights go subsonic and the other flight go supersonic, the drag was different enough that they would go to the same altitude. The supersonic one would slow down so quickly that it would actually not go higher than the subsonic flight. And they actually won the competition from that theoretical calculation. I was proud of them because that was actually my team. But I didn't do the calculation. They figured it out for themselves. We also do quadcopter challenges. And so we call these exploration flying challenges as opposed to like drone racing. So in the case of quadcopter challenges, what we tell people, teams of students, okay, is we want you to build a vehicle and then fly it in an environment, but we're not going to tell you in advance what's in the environment. So we call it exploration flying in a mystery environment. The reason we do this, it's not totally dumb. Basically, I tell people, look, NASA sends things to Mars. And there are things at Mars, but we don't necessarily know what's going to be there before we go. So you have to take cameras and sensors and try to understand the environment. And you might guess wrong in what you take along. But we want you to try to take pictures of and ultimately map this environment, find areas in this environment that are unusual, possibly high magnetic field areas because we've scattered around certain magnets, maybe high or low temperature areas because we have, ice cubes or whatever it is hidden in the environment. But we won't tell them in advance what it's going to be like, other than you need to, as thoroughly as possible, investigate this particular mystery environment. And so here are some pictures from a couple years ago when we did this competition, the first time, in fact. And in this case, which is different from this year, in this case, we had the teams build the quadcopter before they flew the environment. This year, then that was hard. And so this year we decided to skip that part, mostly because of COVID, and it was just difficult for teams to get together adequately enough to build and troubleshoot a new device. So we said, look, instead, use a flying device. It's going to be smaller than this one. And then you have to be very, very, very thoughtful about what you carry on this device because you don't have a lot of lifting capacity. And then go out and do your best to explore it. So this was our exploration challenge announcement for the 2021 year. And there's a photograph actually of the small drone that we're using. And here's actually a list of the schools that signed up. And as of this moment, there were 12 schools. It turns out that we're down to 10 at the present time, but notice Winona State University is on the list, and they just turned in their preliminary design review, a report last week. And so right now there are a panel of judges looking that over and going to give them feedback, and I'm looking forward to seeing what they're able to accomplish as compared to the teams from these other schools. What I want to do now actually is just recap and tell you a little bit more about some build opportunities. So mostly what I've been talking about is aerospace build. It's not the only thing we do. We do curriculum development, and we do, astronomy outreach and lots of things. But this is mostly what I do, and that's why I can tell these stories sort of most effectively. But let me just list a bunch of NASA-themed build opportunities, okay? So for instance, here are 3 projects that I'm particularly involved in. One is the Quadcopter Exploration Flying Challenge, and we'll see if we decide to do it next year. We're going to do something. I'm not sure we'll do that necessarily every year. There's also the Space Grant Midwest High Power Rocketry Competition, which is on hold this year, but we hope to bring it back next year. We'll announce rules for that in the late summer. But if any school wants to get involved and doesn't already do high power rocketry, I would encourage you to contact me or contact somebody at least who does high power rocketry, learn about it, and go through the process of getting yourself up to speed, including possibly getting somebody, if not everybody on the team, certified. There are 2 launch locations in this state that are run by AAA Minnesota. One of them is in North Branch, which is north of the Twin Cities. And one of them is in southern Minnesota. It's sort of halfway between Austin and Albert Lea. So that one might be closer to Winona State. But so those are the places you have to go, since launching of these rockets, which look like weapons and are weapons in some sense, that needs to be supervised by people who are even more certified than me. And then we have the BABS program. So BABS, B-A-B-B-S-S, stands for Build a Balloon-Borne Stratospheric Spacecraft. So BABS basically is a program where I allow people to build payloads, and I offer to fly these on my stratospheric balloon missions for them. I encourage them to show up. I encourage them to learn about ballooning, but you don't, in fact, have to know much about ballooning as long as you know the rules. Like it can't be heavier than this, or it has to be able to survive this environment, or this kind of a shock, or this kind of a pressure drop or temperature drop, things like that. So essentially, this is an offer to build things that are built by other people, and I'll even give you instructions or at least advice about what you might want to build and how to build it. So here are 3 build opportunities that are available to you, and you're already involved in one of them. Here are some more independent projects. Okay, so I guess prior to high power rocketry, you could imagine model rocketry, especially if you didn't do it a lot as a kid, or if you did it a lot as a kid and want to do it more and with more theory. Lots of the lessons and skills are very similar, but these are easier and you can launch these from anywhere. You don't need to go to a very specific launch site. On the other hand, high power rocketry does not have to be competitive. You can certainly do this. Lots of people do this as a hobby. And so, and you don't have to stop with our competitions. Our competitions tend to be on the HIJ scale motors, but other competitions, mostly in the desert Southwest, tend to be much bigger rockets and much higher altitudes and much bigger motors. Stratospheric ballooning is something that you could do in general. You don't have to do it with me, although you might want to try to learn it from someone who's done it, like me. It can be done for research purposes or just sort of for general education purposes. In fact, I think of my my stratospheric ballooning as higher education, general education. But I know lots of people who need to have research productivity, and so they figure out things to do on balloon flights that are research grade. And then the purpose of their flights are to do something over and over again and eventually learn something new and publish it. I'm just not limited to do that, although I will do that myself sometimes. HASP, which stands for High Altitude Student Platform, is a little bit like BABS, except it's BABS on steroids. Actually, put the other way, HASP is the serious program and BABS is a miniature version of HASP. So in the HASP program, you build a payload to fly in a balloon, except this balloon has like an 18-hour flight time, not just a 2-hour flight time like my balloons. It will float at altitude for a long time. It flies out of Fort Sumner, New Mexico, and you actually have to travel to New Mexico or to Palestine, Texas, or both to be involved in the program because that's where the balloons are launched from in New Mexico and where they're tested out in Texas. So there's some pretty serious time commitment to get involved in HASP, but this is definitely a research grade activity if you want to do something in the stratosphere and have a long hang time, relatively speaking. Rock On and RockSat refers to workshops to get people involved in putting things on suborbital rocketry flights that fly out of Wallops. NASA Wallops is in Virginia, and they fly rockets out over the Atlantic Ocean. These particular rockets actually are buoyant, so they land in the ocean and they float and they recover them. So the idea with Rock On in particular is over the course of a single week, you build something and you fly it into outer space, literally, just not into orbit. So suborbital flights, and you bring it home and you look at the data. And then if you want to, you can build your own custom payloads, research grade presumably, and take them back and do the same thing again. And those are referred to as RockSat flights. So Rock On is the introductory workshop, and right now they're signing up people right now for Rock On. And then RockSat is the follow-on activity if you want to get involved in additional things. And then of course, radio controlled vehicles. I already mentioned some of these: drones, fixed wing aircraft, lighter than air vehicles. These are things that could relatively easily be done at your institution by you, but I would be happy to talk to anybody about my experiences more if that would be helpful. Here are a few other more distant college university student competitions. NASA actually has a lot of these things, and they're for various age ranges. They're the middle school competitions, and then they're the college competitions, and those are the ones we watch most closely, like the Human Powered Rover Challenge. There's the Lunar Mining Challenge, which takes place at Kennedy. The Human Powered Rover Challenge takes place at Marshall. They just announced a series of Artemis. Artemis is the new Go Back to the Moon program, and Artemis challenges, including the Lunar Lava Tube Robotics Challenge, which is being run by one of the space grants, the Washington State Space Grant. They're signing people up for that right now if you're interested in robotics. The AIAA does a variety of activities for students as well, including their CanSat project, where you build something that's about the size of a soda can that does various things and is carried on a high power rocket and eject it, and then is supposed to do its mission on the way down. You don't have to do the rocketry, although our teams tend to learn to do the rocketry so they can practice. One of the things that was tried in CanSat a few years ago was, can you have a descending vehicle that generates enough energy so that it can power its own electronics and then send out radio transmissions while it's descending? And you can imagine this could be valuable for you know, a distant landing on a distant planet sort of thing, where you don't necessarily want to have your batteries charged or pre-charged, but rather you want to just say, hey, we're moving fast through this atmosphere. We can generate a lot of energy because we're moving fast through the atmosphere, and use that to do various parts of our project. And then AIAA also does flying vehicles, their design, build, fly competitions. I encourage you to look into those as well. Okay, so here's what some people have been waiting for. How can you get involved? And I've given you some clues, but let me just give you a list of things. Okay, so one is what you're doing right now. Talk to us, talk to people, learn who's involved, contact the people who are already involved, figure out what they might be willing to do as far as collaborations. We have a student symposium coming up in March. And so if you want to hear students talk about the projects that they've been doing, that would be definitely an opportunity. Tap our expertise. Basically, we've tried a lot of things, and some have worked and some maybe not so much, but you could attend a training workshop. You could pick my brain or others about classes that we've tried and how well they've gone. You could start a extracurricular team, like a high power rocketry team, stratospheric ballooning, both of which require some startup and some training, but we can provide that. And then you can pursue opportunities that are already open. For instance, and this is one of the things we do, we spread news about opportunities, like apply for NASA Center internships. This application process is going on right now. And so if you want a NASA Center internship for this coming summer, get your materials in right away. And so the Minnesota Space Grant sometimes is asked by NASA mentors to fund students who are going to school in Minnesota. And we don't care in this case whether or not those students are from our consortium schools or not. We fund people until we run out of money. You could participate in the activities that we already do. I mentioned some of them, including our Midwest High Power Rocketry Competition, the BABS program, the quadcopter competition, which you're already involved in. Or you could sign up for some of these other activities that are run by other space grants, like HASP, like ROCK-ON, like the Artemis Lunar Lava Robotics Challenge. Those are run by other space grants around the country. On the other hand, on our website, in the Opportunities tab, it actually says people outside of our consortium are allowed to ask us for money. Not a lot, maybe, but money, okay? And so this is just a straight quote. It says, mini grant funding, up to $5K per project, can be considered from proposers outside, especially if it's for things that we are not already doing, but they're well aligned with our goals. So understanding our goals is important, of course. And one of the goals will be engaging more women and more minority students in NASA-themed activities. And these projects must have match so as to make the money go farther. And I already mentioned this, the scholarship area and the research area are limited, somewhat limited, especially in the case of research, to activities that would be funded or at least proposed by our people, but possibly could involve collaborators from outside. And then last but not least, you can certainly explore, and we've actually started some of these conversations already, the possibility of becoming a formal affiliate. On the other hand, I think the way to do this, although I'm open to the concept, is to try some of our projects and show us that you're good for it. In other words, that you actually can bring value to the consortium, in particular doing things that we are not doing or we are not doing enough of. A couple things that come to mind right now are teacher workshops. I think we could benefit from more people willing to offer more teacher workshops. Also, perhaps more programs, we have some, but not enough, I think, to engage underrepresented minority students and get them into college, like 2-year to 4-year transition students or students in high schools who want to go to college, and maybe bridge programs that give these students some college experience during their high school years, which is allowed. So these are a couple things that I would consider as possible openings, not necessarily easy openings, for Minnesota Space Grant activities or funding from outside of the consortium for proposals. So I'm going to end here. I'm just going to leave up the following slide. This is a poster. This poster is up in our building, and it basically just mentions who is involved in our consortium, who we also work with informally, pictures of lots of people, lots of activities. I've even showed you some of these same pictures already. And what you have to expect with respect to match, who to contact, things like that. So go ahead, and I realize it's an eye chart, but read through that if you want to, but I'd be happy to stop now and take questions. And Demos, again, is on the line, and he would be hopefully pleased to take questions as well. In fact, Demos, do you have any comments about things you think that I may have skimmed over or missed, or you would like to clarify?
Nope, you covered it pretty much completely. So if folks have questions, I am here as well.
Okay, so again, I'll just leave this slide up for the moment. Actually, I might skip to stop sharing my slides, but let me do that. Let me.
Well, great. I think those of us who are able to make noise can do so. Thank you very much. Just want to remind everybody that if you've got questions, please put them into the Q&A window, and Dr. Beardsley and I'll get to those. Go ahead. Do you have anything to start with, Adam?
Sure, I can ask a question while we wait for students to type in.
Can I ask a question? Actually, this is a technology question. Now that I jumped out of my slide deck, I don't see any evidence of Zoom on my screen, so I don't know how to stop sharing. I was hoping to stop sharing, but I don't see any Zoom on my screen. Anybody?
On your bottom taskbar, I can see the Zoom. There you go.
Oh, somebody else did. Somebody else. You killed me. Okay, that's fine.
I'm sorry. I'm
No
sorry.
problem. I'm
Your
happy.
time in the stratosphere was over.
I was stuck, so thank you. Okay, we're happy to take questions.
Yeah, so I'll ask a question while we let students think and enter something in. I was curious, I've never done any kind of ballooning myself, but you mentioned, trying to drive west so that balloons don't drift into Wisconsin, into a wooded area. So like, what does retrieval look like? Do you just go track it down and then start knocking on doors if you have to go into somebody's yard or property?
Sure. So basically, the answer to that will vary depending on where you live in the country. I've been told by people in Louisiana, you don't just walk into people's property because they have guns, and it's like, okay. But no, in actuality, people are usually very curious about what we're up to. We have trackers on it, so we know exactly where we're going. We might show them. In fact, the last time I did this, something landed out in a field behind someone's property, and I went up to their door and I showed them on my phone. It's like, look, this is where it is. I just want to walk out there, and they said, go for it. So generally speaking, people are completely interested. In fact, though, it's more likely you don't find any people, because we tend to fly these things and land them where there aren't lots of people around. And if I don't find people and I know it's right over there and I could get there and get back before anybody could possibly catch me, then I usually just go and grab it and go home.
Makes a lot of sense.
Tracking is very important, though. You need to know where you're going. If it lands in a tree, we have techniques for getting things out of trees. And if push comes to shove, and this did happen to me a couple months ago, I literally hired somebody to climb the tree for me because it was 90 feet up, and my abilities stop at about 80 feet. So 90 feet up, just give the guy a bit of money and he'll climb up and grab it. It's like, really? Okay. So knowing somebody who's done it before and can give you advice is a good thing when it comes to ballooning.
Yeah, for sure. So it looks like we're getting a few questions showing up. One of them, if you guys don't mind, put your questions in the Q&A box, but I did see one showed up in the chat. So I'll read that to our speaker. I read you include particle counters on some balloon flights. Can you say something about the purpose? Are high altitude particulates tied to climate change?
Okay, so the answer is sort of. Basically, the fact that we fly optical particle counters, which is true, is related to a research project. And so this is a collaboration that I do, since I do ballooning, with other faculty in my own department who are interested in understanding the stratosphere for purposes of designing better hypersonic vehicles. So it turns out that when you fly hypersonic vehicles at 100,000 feet or so, at Mach 7, sometimes the airflow over them goes turbulent, and it's not always clear why. But if it goes turbulent, you have heating problems immediately. And so one of the possibilities is that it's because there are particles up there, and if only they understood the particles better, they could feed them into their simulators and design better vehicles. I think it's unlikely that that's going to be the problem, but that's the reason for the research. It's not actually related to climate change. On the other hand, obviously, you can access not only the troposphere, where essentially all weather occurs, but the stratosphere, which is in fact important for weather, with these flights up to maybe 120,000 feet, depending on how you play your cards. And if you did this over a long enough period of time, you could notice effects of climate change, no doubt.
Cool. Thank you for that. Let's see, the next question comes from an anonymous attendee. How long do your balloon projects last? I don't know if they're asking about the project itself or the flight.
Okay, well, I'll answer both. One thing I really like about ballooning is that you get to build something and fly it, and if it doesn't work, you could potentially rebuild it and refly it within a lifetime, where a lifetime is like the course of one semester class. As opposed to, you know, if you're going to send something to Pluto, you get one shot, and that's it, and it takes years to get there. Or if you're going to send something into outer space, maybe it takes not so many years, but anyway. So I like ballooning in particular because it's really like spacecraft, but you don't have to spend a lot of money, and you can do it more than once, and you can do it over the course of a few days or a few weeks. So I will often, you know, do this as a several weeks project, or maybe even a full semester project in a class. On the other hand, the flight itself is a day-long event. So typically we get up fairly early, we go out, we might drive out of the city a couple hours at least, launch our things. It takes maybe a couple hours to get them up in the air just because of all the setup and details. And then they're in flight for 2 to 3 hours. And then once they've landed, it may take an hour or 2 or 3 or 10 to get them back, and then you drive back. So basically 12 hours is easy. Less than 12 hours is lucky, and more than 12 hours is not uncommon for a balloon flight. It can be a long day, but it's in one day. You get the thing back the same day you fly it. That's how I do business, at least. So what that means, though, is that pretty much this is a weekend event, at least during the school year, so that you don't have to take people out of classes. On the other hand, I also have a summertime ballooning team, and we typically will spend one day out of every week or every second week or so out on the flights, and those would be during the regular work day, just because this is the job.
I'll ask the next question in the Q&A to sort of follow up with this. So the question is, what is the highest that you've gotten a balloon? And then I'll ask sort of a similar question, which is, what's the farthest that you've had to go to recover it? Because I assume you have to get as much of it back as possible. So maybe depending on wind speed or whatever, but can you give us some ideas there?
Okay, so 80 to 100,000 feet is a standard altitude for like a 15 or 1600 gram balloon with up to 12 pounds, which is what you're allowed to fly without special permission from the FAA. If you want to fly heavier things than that, you need special permission, and you need to sign off that you won't fly if it's cloudy. And unfortunately, you don't know that it's cloudy 6 weeks in advance when you have to ask for the permission. So I really try to stay exempt. I try to stay below 12 pounds. On the other hand, if you take these same balloons and only fly a couple pounds worth, and you need to fly at least a parachute and a radio, otherwise you won't know where they went, you might be able to get above 120,000 feet. I think our highest flight ever was 128,000 feet. I know some people who have gone slightly higher, but that's kind of the limit for latex rubber weather balloons. As far as how far they go, I guess it depends a little bit on how well things happen. If they go up and they pop and they come down, they won't go far. Not far meaning 50 miles is a short flight, 150 miles is a long flight, but it's quite possible. On the other hand, if for whatever reason they don't pop or don't pop right away, they can go far away. We landed one in Pittsburgh, outside of Pittsburgh one time. And I know that because they called me from Pittsburgh and asked me if it was mine. We landed one in Idaho, a different time of year when the winds were in a completely different direction. And so usually we don't get those back if they go far away. This is not common, but it can happen. On the other hand, it turns out there's a completely different kind of ballooning. It's called pico ballooning, where you use a balloon that doesn't pop, like a Mylar, 1 meter across balloon or something like that. And if you play your cards right, you can actually get these balloons to go up to about 40,000 feet and park. and they can actually go around the globe more than once. I think 7 times around the globe is actually the record. You don't get those back either, but you can actually have transmitters that will continuously transmit information from these things over the course of months. I've never dabbled in that kind of ballooning, but I know people who do it. And so there's really no limit in some sense to how far these things can go. There is a limit to how far you can go to recover them. And you just have to, in fact, I know people who, if it's going to go more than 50 miles, they won't launch. And it's like, really? So basically 50 miles is a short flight to me, but 50 to 150 miles is fairly typical. If it's 50 miles, you might even be able to be there when it comes down and see it land. If it's 150 miles, you'll struggle to keep up, but hopefully you'll get there shortly after it lands and recover it the same day.
Cool, thank you.
I'll read the next question. Do you have a favorite, do you have a project or flight that you would classify as your favorite or most interesting data recovery you've had?
Well, I have to say that Eclipse project was pretty cool. And that 360 video that I showed you was pretty cool. And frankly, we have that camera, and that was the best it ever worked. We struggled with it before and we struggled with it after, and it just worked pretty well on that one flight, and I was very pleased by that. So that was very cool. Unfortunately, you can't have an eclipse come by every day of the week. I sometimes compare rocketry to ballooning. It turns out that rocketry tends to be an easier sell because people kind of know what you're talking about. They might not be familiar with the scale. You have to build things tough. And so in some sense, rocketry is more of an engineering challenge, structural engineering challenge. Ballooning, on the other hand, you have hours to take data. And so I think of it as more of a science project. I'm a scientist, actually, not an engineer. So I tend to favor ballooning over rocketry, even though it's a little harder to convince people that it's cool. But once they see it, they usually say, hey, that was pretty cool.
That's great. I had a question actually about one of the images, the image of the shadow of the moon from the solar eclipse flight. There looked, so you could see the nice big circular dark part. And then there was actually kind of a lit up illuminated part in the middle. Were you actually seeing like city lights? Was that sort of like, you know, when you fly at night?
Yep. So when you fly at night, you see these bright patches. Yes. Well, these were bright patches of city lights coming on in the middle of the daytime. So that shadow was about 70 miles across, moving at about 1,600 miles an hour. And yes, indeed, it went over the top of various towns, and you could see that happen.
Oh, that's fantastic.
On the other hand, you noticed it was pretty cloudy. And so the people on the ground were not necessarily getting a great view. And so I kind of told people, you know, I would like a really good view too, but I'm less worried because I'm going to get a good view. At least my balloons will, for sure. But on the ground, maybe not. So it was kind of hit or miss. The temperature changes actually in the atmosphere because of the passing of this shadow actually can induce precipitation. And so sometimes there's literally a storm, a rainstorm that follows the eclipse underneath it. And of course, everybody's really disturbed if it clouds up and starts to rain right during the eclipse, but that's not totally a coincidence. Eclipses can do that.
Very cool.
Any more student questions out there?
I have another one. Do you have one more? Do you have another one, Adam?
I do have one more that I thought. What's that?
Go ahead.
Okay. Yeah, so you mentioned that people can tune into the student symposium on March 27th. Will the connection info be on the Minnesota Space Grant website, or how do we connect to that?
I'll try to remember that you're interested, but you should probably ping me. And yes, we're still organizing that, so we haven't decided. And we might have double streams, as in not all talks in just one long day in one channel, but rather multiple channels. But no, we're completely open to people watching that. And I have a committee that's tasked with helping me organize that, and we haven't met yet, but we will. And so we are going to sort out how to do that and how to post that and how to share the information. And so why don't you ask me again in mid-March, and by then I will know for sure, and probably your asking me again will remind me that, oh yes, I should put this on my website too.
Sounds good. Thank you.
Excellent. I just wanted to, since some of the people who are attending this are teachers or future teachers, I assume that if they are interested in some of the Minnesota Space Grant teacher workshops and things, they can also go to your website to find sorts of trainings and courses and things, and they might be able to contact you if they were interested in a few years.
Almost correct. The almost correct is that we don't necessarily post on our website our schedule, but rather we say, here's what we do. If you'd like more details, let us know and we'll be in touch with you. So yes, going to our website would be fine. Here's something, the last thing I did literally before the COVID shutdown last year, on the Saturday that everything shut down and we didn't restart on Monday of that week, was I had a workshop with 13 physics teachers from around the state. They weren't all from the metro, on ballooning, and we just never got around to ever building and flying any balloons. This was a workshop talking about ballooning and what we were going to do later in the spring with their classes, and it didn't happen yet. So yes, indeed, I need to get back in touch with those teachers. Those were physics teachers, actually. But if other students, whether they are in-service teachers or pre-service teachers, I'd be happy to talk to them.
Cool, great. I don't have any other questions right now. Adam, do you have anything else?
No, just
Okay.
I'd like to thank the speaker again.
Yeah, this was really great. Thank you very much